Welcome to our video on op-amp transfer functions. In this video, we will be looking at the inverting and non-inverting amplifier configuration. So for both of these, we're going to do the derivations, the properties, and we're going to do some simulations to make it a bit more visual. And after that, there is a self-test problem where you're going to do the derivation, the design, and simulation of an amplifier with a bit of a different feedback configuration. So first up, we have our non-inverting amplifier. So let's have a look. First, you always write down the assumption. Okay, so the currents flowing into the amplifier we assume is 0, so there is nothing flowing in. Second up, the inverting and non-inverting terminals is the same, and the non-inverting terminal is connected to Vs. So this point at the inverting terminal Vn is also Vs. Okay, now to find the transfer function of the amplifier, we need the output in terms of the input. Okay, so the gain of the amplifier is the ratio of these two. Right, as denoted on this side. So, if we have a look at these resistors, since there is no current flowing in here, we don't need to worry about anything at this node. Okay, but if we view V out as a voltage source and we are trying to find Vn or Vs, we are dealing with a plain voltage divider. So Vn is a voltage division across R1, which is also Vs. And if we rewrite this to be in the form of V out over Vs, we get that the gain of this amplifier is 1 plus R2 over R1. Right, so this amplifier has thus the properties of the gain is defined by the resistor ratio R2 over R1 plus 1. And if we have a look at our amplifier at the input, our input impedance is infinite, denoted by the input impedance of our op-amp, and the output impedance should be close to 0 in the ideal case, and the input will be increased and the output will be further decreased with the application of our feedback resistors. And the non-inverting amplifier is our purest form of a voltage amplifier for op-amps. So let's go and have a look at this amplifier in LT Spice. So in LT I constructed the amplifier using ideal op-amp or universal op-amp 2. I added rail voltages of plus minus 10 volts, made a simulation for 10 milliseconds, and I'm putting through a 1 kilohertz signal at 100 millivolts input. Okay, so R2 is 10k, R1 is 1k. So this simulation should give us an answer of 1.1 volts peak out, because the gain here should be equal to 11. So let's run this. We check the input, 100 millivolts, look at the output, 1.1 volts, and there is our amplifier working nicely. Okay, so it's nice to see this or visualize it. The second thing that I want to show you is that ideal op-amp, we can actually approach the rail voltages. So the maximum for this signal should be plus minus 10 volts. So let's go ahead and increase this to, let's say, 1 volt input. Run it again, and immediately you will see clipping on our signal. So here is our input, and our output is being clipped or saturated at plus minus 10 volts. You can also see the input and output is not inverted from one another, so they are actually in phase with one another. That is it for the non-inverting amplifier. Next up is the inverting amplifier. Now, the inverting amplifier, we can see that the non-inverting terminal is grounded. So this is at a voltage of 0, so this node right here is also at a voltage of 0. So Vn is equal to Vp is 0, and as always we assume our currents flowing into our amplifier to be also 0. So the inverting amplifier we can take a look at using Kirchhoff's current law. So if we take this node, the current flowing through R1, the current flowing through R2, and the current flowing here is 0. If we take the sum, that should be 0. Convert that using some node voltages. Then Vn is also 0. So we can find Vs and Vout in terms of one another. And finding Vout over Vs gives us R2 over R1 with a negative sign here, which denotes that our output will be inverted from our input. Now, if we take a look here, we will see something very interesting. This voltage source is divided by R1. This is this IR1 right here. This shows us that this amplifier is actually a trans resistance amplifier. The input impedance at this point right here is 0. So this amplifier would gladly accept the current. So the purpose of Vs and R1, or R1 rather, is to convert this voltage into a current to put into our amplifier. Okay, so this amplifier is actually a trans resistance amplifier with a resistor to convert our input to a current. Okay, so this amplifier, R1 is our input impedance, not infinite, because the input impedance at this point right here is 0. There is nothing there. So R1 becomes our input impedance, and Vout is still the same as the previous problem at 0. So it's actually a trans resistance amplifier. The gain is inverted, but the ratio of R2 over R1, and the input impedance is R1. Okay, so making or giving R1 here actually makes it a voltage amplifier again, because we're providing a voltage and getting out a voltage. But without R1, it's a trans resistance amplifier. Okay, so this input right here could be something like a photodiode, which provides a current. So if you have a sensor that provides a current, this amplifier is a good one to use. So next, let's take this into a simulator. So here I'm using the same setup as the previous problem. 10 volts rails, 100 millivolt in, 1 kilohertz, simulate for 10 milliseconds, and our gain is R2 over R1. So the gain for this amplifier should be inverted 10 volts per volts. So if we run this and take our input 100 millivolts, take our output 1 volt, and you can see that they are 180 degrees out of phase, and the gain is exactly 10. So let's increase this to 1.1 volts, run it, and you will see that we again drive it into saturation if we do that. That is it for the inverting amplifier configuration. Next up is the self-test problem. So I want you to pause the video and take this amplifier with this free resistor feedback network over here and go and analyze the amplifier and find the gain equation. So I want V out over Vs firstly. Then I want you to design this amplifier to have an input impedance of 2.2 kilo ohms, use R2 as 22 kilo ohms, 3 different values for R3. This means that there is 3 different values for R4 that you need to design for a gain of 100 volts per volts. And I'm saying absolute here because this is clearly an inverting configuration. Okay, so this is going to be a minus 100 volts per volts. And I want you to provide E12 values for the resistor values that you choose. And note down the effect that you have with a change in R3. So for every R3, you're going to have R4 value, and see if you can make any notes on changes. And afterwards, I want you to simulate your result. So go ahead and pause the video, do this self-test problem, and when you're ready, you can unpause the video and look at the results, and I will quickly discuss it with you. So the solution to this problem is we can make the same assumptions that we've been making for the inverting amplifier configuration. So this node here is at 0 volts, and we can say that the current flowing in these two resistors towards this node with Kirchhoff is equal to 0, the sum, and you'll find that the ratio of resistors gives you the same as the inverting configuration. Then here on the second node, we take all the currents flowing out and take the sum of those being equal to 0, and then set up the equation for V3 here minus 0 over R2, V3 over R3, and V3 minus V out over R4. We end up with this equation, so this 0 can fall away, and V3 we already have in terms of Vs. So for this inverting thing, we can just plug it in here at the beginning, so we can take out all of these V3s and just replace it with this inverting configuration. And V out over R4 can go over to this side, and we are left with V out over R4, the inverting configuration, and 1 over R2 plus 1 over R3 plus 1 over R4. Multiply with R4, and we will have R4 over R2, R4 over R3, and R4 over R4, which is 1. And we will be left with this equation right here. So let's go and have a look at the design part and the simulations. For the different R3 values, you will find that R4 has a couple of values, but none of them are actually close to the E12s for selection. Okay, so I put in a fourth one where I worked through the ratios to find something that has proper E12 values connected to them. So the results is 10K, 68 and 180 Ks. So each one of these will have a much higher gain than that we designed for if we choose the E12 values. Okay, but the thing to note is, in general with the inverting amplifier, it is R2 over R1 is our resistor values. So the resistor, if it's only R2, would have been 220 kilo ohms. All of these resistors are much lower, especially here where R3 is a much lower value. So we can achieve a high input impedance and a high gain using smaller resistor values if we use this configuration. Putting this into the simulator, I took the 1K R3 and the 10K for R4 and an input signal of 10 millivolts peak. Let's run this. There's our input and there is our output. So with the slightly larger choice of R4, you will see that this is a much higher gain that we achieve. So for the E12s we have a much higher gain. 8.6K if we're not using the E12. There's our gain exactly at 1 volt peak, or our gain is exactly at 100. And you'll find that these resistors here is much smaller than 220 kilo ohms. But you have 3 resistors now and not just 1 resistor, so there's a bit of a trade-off if you do this. Okay, let's check the ideal case that I simulated or that I designed, which provides much better resistor values. And this was done with a 6.8K here and a 47K here, if I remember correctly. Let's run that, and our gain is 100 and our resistor is also still very small. So you can find the transfer function of any resistor configuration around op-amp, and if you just change small values and make observations about your changes, that can help you with designing in the end. It's always about observing what the change brings to the table. So That is it for transfer functions. Thank you for watching.